Hey, Mr. J here with our lesson for section 2.1 or module 2.1. And it is about writing conditional statements, which are really if-then statements. And I'll make sure that's clear to you by the end of this lesson, I hope. And you'll get some practice out of your textbook on this. Before we dig into that, I wanted to give you a little more context on where this is coming from in terms of the flow of the textbook here. And we are in this unit called Essentials of Geometry. We did the basics here of Module 1, Geometry in the Plane, and now we're doing Module 2, which is all within Unit 1. And then we'll move on to Unit 2, which will have a few modules. So this textbook breaks things down a little bit further than your typical textbook, and we'll have to make an opinion or have an opinion on whether that's working for us or not. But I want to jump into first an overview of a nice problem to introduce us to conjectures and conditional statements. And we can do that by looking, this is the first page out of your textbook, and it says focusing on STEM and scientific reasoning. And I have to tell you, I read this here and I need a science teacher to help me out because it talks about a geoid model and gravitation anomalies and this thing here. What was it called? Pseudo color images. It sounded fascinating to me, but really I don't need to dig that far into that. Let's dig further into what I care more about is interpreting graphs. Okay, and so they graphs I can look at and look at points and try to make a conclusion from that. And I see weight is on one side and mass is on the other. And I know we can't confuse weight and mass. Your science teacher would get upset with me. And I'm not going to get into those details. That's a question for your science teacher. But I still think we can interpret these points. And it really does look like you're getting a bunch of data. And isn't it following a straight line? Can I draw a line here that follows this data? A line of best fit? It looks very linear to me. Very linear, like a linear equation. And that means we could find both a y-intercept and a slope. And so maybe we could form a conjecture. And conjecture is really, and we've talked about this a little bit before. I didn't mean to cross that out. I meant to highlight it. A conjecture is a hypothesis. It's something you think is true. You don't know. You want to investigate it. You want to find more data and see if you can prove it to be true. And that's where it relates to geometry because we are about proofs in geometry. So we want to explain our reasoning, and I'm not going to dwell on this too long, but a possible conjecture here is that the weight of an object is about 9.8 times its mass in kilograms. So if we look at the weight on the left axis, the y-axis, and compare it to the x-axis, you'll see it's about 10 times. You see the 6 and 60 and the 10 is close to the 100. It says it's 9.8 times. So they're being a little more precise than I might be. And so for each time we go up 9.8 on the y-axis, we go over 1 on the x-axis. Seems like an interesting thing to relate weight and mass. Okay. Now if we're going to write that as a conditional statement, it says write a conditional statement, that just means taking your conjecture and putting it in an if-then form. If the mass of an object is x kilograms, then the weight is 9.8 times that value, 9.8x. Seems like a good conditional statement. And we could find additional data. We only have a limited set, a finite set of data right now. And we can't actually prove anything this way because there always could be one more example where the dot would be somewhere else. Can you picture how there we could get somewhere else and the mass of the object was maybe over here? And so that would prove it wrong, right? So that's the nature of science and even like research into vaccines that we're all caring about now. Are we going to have 100% validity? Or are we looking for just significant validity between the efficacy of a vaccine? So no, a conjecture cannot be proven correct by a finite number of cases. It can't be proven to be true. But in math, we're going to be looking at things that we can prove to be true. And I think in D, they actually do find a counterexample to prove this conjecture or this conditional statement false. So I kind of liked how they introduced this here. We're going to move on now and just look at the overview here. I'd already put this up there, the right conditional statements, and how we'll do that, and some vocab. As you have been told, geometry is very heavy in vocabulary, and you're going to need to keep a glossary, check the vocab before a quiz or test, keep adding new words, make sure you're ready to learn words like contrapositive or converse or counterexample, and you'll see why that's important as we get further into the year. Okay, the use of an if-then or conditional statement is a common form of argument that is used not just in geometry but in other areas of math, science, and everyday life. And I like their example here at the end where they said, you know, if you don't study, did I not get the pen here? Well, if you don't study, then you will not do well on the exam. That's a conditional statement. You can decide whether that's true or not, but I want you to understand that format there of a conditional statement. Let's move ahead. All right. So I'm going to hide these right now because we don't need these yet. I'm going to talk about them in just a second. So here's a conditional statement for us to talk about. If I am a Pheasant student, then I am a boy. We can debate that, but yeah, that seems to be true. Do you agree that that is true? I heard that back in the 1910s or 1920s there were a few girl students at Pheasant, but in general I think this is true. Now the converse of this, let me just rewrite these. The converse of this is when we're going to flip-flop. We're going to change the order of it. So that means that instead of the I am a boy coming at the end, all right, we're going to put that in the beginning and say if I am a boy, then it's going to become then I am a Pheasant student. Now I think you can be clear that that is not true. Do you agree that that's not true? Excuse me there. Right? The first one seems true. The converse is not always true. There are, people that make arguments out there that try to get you to believe that converses are true, but converses are not always true. All right? And then we're going to go to what the inverse is. The inverse is you're going to take the first statement here. You're not going to switch the order, but what you're going to do is you're going to negate it. You're going to put not here and then not here. If I am not, I think I put the A in the wrong place. If I am not a Pheasant student, then I am not a boy. We can debate whether that's true or not. I think you'll probably say that that is false. It's definitely false. But inverse means negating that NOT part, right? Maybe we can underline that so it's clear. Okay, that's not, this one's not. Okay, the contrapositive does both of these things, the converse and the inverse. So let's take this one here because that already did the converse piece, and then let's put in the negation part again because that's the inverse piece, right? So let's debate whether that's true. If I am not a boy, then I am not a Pheasant student. And I'll tell you right now that the contrapositive, right, and the original statement follow the same truth value. If this one's true, then this one must be true. Okay? I'm also going to tell you something else here. Let's talk about what's the hypothesis and what's the conclusion again. So the original part here is the hypothesis. Let's make that the green part. And then the blue part is the conclusion. And let's get those lines just right. So that part there is the hypothesis, and this part here is the conclusion. Now what happens is the converse was the reversal, right? And I think it's nice to see these colors sometimes. So I'm going to duplicate that and say, there's the boy part, and here is the green part. So that just evidence of that flip-flop. And we also use letters sometimes. And we're going to use, let's go ahead and use, this is P for hypothesis, and this is Q for conclusion. And then the Q is here, and the P is here. It's just a little bit of notation, logic notation. And then if we do, I'm not a pheasant student, so this is going to be not. So it's a little squiggle, then P, then not Q. The squiggle just means not, okay? Not P, then not Q. And this will be if not Q, then not P. The notation's not that big a deal, but you might see it places. So if P, then Q. Why do we use P and Q for hypothesis and conclusion? I don't know. I know P and Q follow each other in the alphabet, and that's the best answer I have for you. All right, we have a little bit more that I wanted to talk about. And it's about this, if I'm from Boston, then I'm a Red Sox fan, and that's the if P, then Q. Now, if we're going to change the order, think about what the converse will be. First off, do you think this is true, this first statement? Pretty much. Probably, there are definitely people from Boston that are not Red Sox fans, but yeah, for the most part, it's true. And then the converse will be, if I'm a Red Sox fan, then I'm from Boston. I can definitely think of a counterexample to that. And the inverse would be, if I'm not from Boston, then I'm not a Red Sox fan. So we can talk about that too. And then the contrapositive, see if you get this one right. Can you do it in your head right now? Remember what we do? Swap and negate. So it would be, if I am not a Red Sox fan, then I am not from Boston. And you can expect the next class that we have after this, I'll expect you to do these for a conditional statement. So please study what is a conditional statement, what is a converse, what is an inverse, and what is a contrapositive. All right. I have one more thing I wanted to talk about. Postulates, we'll get into postulates a little bit more and how we make those into conditional statements. We've already talked about counterexamples that prove them wrong. And I wanted to talk about something called a biconditional. And biconditional statements are ones that are definitions. So when I think biconditional, you see this line right here, very important line. It says any valid definition can be written as a biconditional statement. And that's where all of our converse, inverse, contrapositive, they all match in their truthiness, in whether they're truthful, because they're based on a definition. Let's think about two lines intersect to form a right angle, then they are perpendicular. Well, that's a definition. Don't we know that right angle and perpendicular are almost interchangeable? So if two lines intersect to form a right angle, then they are perpendicular. If two lines are perpendicular, then they intersect to form a right angle. This is a definition. And if it follows that it's a definition, then we write it in a special way, and we use this if and only if. Two lines are perpendicular if and only if they intersect to form a right angle. So that's what I want you to think of. When you see biconditional statement, think if and only if. And this is sometimes abbreviated as IFF. If and only if. I don't know, that's a weird abbreviation, but I didn't make it up. So overall, I think that's enough for us for today. We'll spend 2 days, I think, on this first part of Module 2, conditional statements. But I hope this is helpful. Have a great day.